Hey, so this is a new experiment where I want to see what happens if I try recording myself doing some research. This also kills two birds with one stone, because I've been writing a transformer interpretability library called Easy Transformer, and I both want to test myself, is this actually any good, and I also want to produce demos for it. And so I thought it'd be a fun exercise if I pick a small self-contained research thing and then go to try to solve it and see what happens while vaguely monologuing and trying to narrate my internal narrative of what I'm doing. This is entirely an experiment, so I'm very curious for feedback on was this worth doing, is this remotely useful, and what people's perception of this is. But yeah, so the question that I'm trying to answer today is, what happens if you don't give a transformer positional information? And so a friend asked me this question, and this is kind of weird, but because so naively in a transformer, every position is symmetric, and so there's no inherent way for the transformer to know things are nearby. But if you have a causal attention pattern, i.e. things can only attend backwards, it seems like the model should just... Well, if you've got a causal attention pattern, the model is... If you've got a causal attention pattern, symmetry is broken, because things near the start can attend to fewer positions than things near the end. And this means the model has some information, and it seems plausible to me that it could use this information to rederive positional encodings for itself. And I'm not sure there'd be any deep implications of this, but it seems kind of interesting. And it would also just kind of entertain me if the correct answer to how to encode positions into a model is, I don't know, it can rederive them, it just saves it effort if you tell it. So, yeah, I want to go and try and investigate this. So I should probably increase the font size in the hopes that this is legible to people. So, how to investigate this? I think that... Sorry, let me just go and fix some dumb technical issues. Great, sorry, dumb technical issues fixed. So, yeah. Don't really have any particular claim this is a useful question to answer, but it sounds fun. So, okay, so the first question I gotta ask myself is, what is a reasonable way of trying to answer this question of, can models figure out positional embeddings on their own? And it seems like probably the cleanest way of doing this is coming up with a simple, small transformer on an algorithmic task, where the algorithmic task inherently requires it to know things about position, and then to A, verify that models without positional encodings can successfully do this task, and then B, try to go inside and interpret how it does this, and see if I can learn anything interesting about how do positions work inside models. So, yeah. So I had a bunch of ideas for what the dumbest task for this could be. Sadly, most of them involved changing the transformer architecture in ways that would kind of be a pain and break a bunch of my code. So the idea that I came up with that seems both interesting and least code-breaking is I'm going to train a model on a sequence of random tokens, and then I'm going to train it so that for each token, it has to predict the token before it. Note that this is completely different from the predict the next token. Note that this is completely different from the predict the next token loss function. Because this is actually some, like, weird crossing over thing, but... Or, okay, let me just actually draw a quick diagram, because this is probably actually mildly worth doing. So, what is the task I have in mind? So, the task I'm imagining is we've got some tokens, say A, B, C, and D, and then for each token, I'm training it on its ability to predict the previous one. So for like B, the ground truth is A. For C, the ground truth is B. But importantly, because this is causal and they can only look backwards, C can see A and B and C, but not D. B can see A and B, but not C, etc. So it's kind of the opposite of the predict the next token task, where it can, like, in some sense, exactly see the information that matters, and not all the future information that's completely irrelevant. And if I make all of the tokens just uniform and random, this seems like it should basically isolate out the concrete... Yeah, this seems like it should basically isolate out what the model is doing to figure out positional information. And the final thing is just like, what do I think the model might learn how to do to this? Where the kind of a natural hypothesis for a thing that it might be reasonable to do if you're a model is, so in a world where we train with like a kind of special start token, I don't know, let's just denote that with some magic symbol. So often people train models, so they've got a special start symbol here. Often people are sad and don't train a model to have a special start symbol here. It seems like one algorithm you could use if you do have a start symbol is to have one head that just learns a uniform attention pattern over all previous things. And this means that the head at, say, position 5 will have a 1/5 attention to everything. Then the OV circuit for that head learns to copy the value of just the start token and ignoring everything else. In which case, it's getting out the head is going to have the same result every time, but it's going to have like a different magnitude. And then the model learns to do some mysterious voodoo with that fraction of 1/n in some direction to convert that to a notion of what the position actually is. And this seems like a weird fucky task, and I predict this is the kind of weird fucky task that is a lot easier to achieve if you have an MLP, if you have MLPs. And so my advanced prediction going in is that a sufficient model to do this will be a model with a start token and 2 layers of both attention and MLPs in each layer. And I predict that the natural algorithm will be something like learn to find a direction corresponding to the start token and a fraction of 1/n, learn to do some fuckery with MLPs in the first MLP layer to convert that to some notion of position, and then use that in the second attention layer to attend to the previous position, and then just predict things from that. And so this predicts that the minimal required architecture should be, so drawing a diagram, what it predicts is going to happen. We've got this token embedding. We've then got one attention layer, which I predict is going to be doing approximately uniform attention to the start position. Man, having a graphics tablet is great, but it doesn't make my handwriting not suck. Then we have an MLP layer, which I predict is... And so I predict the output of this attention is going to be 1/n in some direction. Then I predict the MLP is going to sharpen this somehow. And then there's a final attention which does previous token attention. And then, I don't know, second MLP layer, which is probably not really going to do much, because if you know which token to attend to, it should be pretty easy. Okay, that is my advanced hypothesis. I'm now going to go train a model and see if this hypothesis is completely wrong or not. Oh, I should probably get rid of these shapes. Do I want to get rid of these shapes? Let's go with yes. Okay, so how do I do this? So first I have the incredibly hacky and cursed code setup where I got bored of just copying and pasting all of my standard imports into every file, and so instead I've got this glorious library called Neil imports that just contains everything I might ever need. And my intuition says this is terrible code practice, but whatever. And so let's just map out roughly what I want my code to look like. So setup area where I do like imports, define, so I want to do model training, and I want to do model interpretability. Within model training, I want to have setup, and then actual model training. Within setup, I'm going to have defining the model, and yeah, I'm going to want to define the model, and I'm going to want to let me just clear out some more screen space. Yep, I'm going to define the model, and I'm also going to define data and loss function, actually train the model, and probably going to break down model interpretability into look at attention patterns and see if they're doing something broadly sensible. Look at how different bits of the model directly contribute to the logits. And I don't know, if my hypothesis is correct, try to interpret MLPs. Alright, so that's roughly my game plan. So, setup, defining the model. The way I have my library set up, I just define a config function, which just takes in a bunch of transform parameters. So here, I want to have a 2-layer model. Let's say the width is 64, and I probably want to just give it, let's give it 1 head per layer, and see what happens. I need to tell it how many MLPs it has, and I don't know, let's default to the standard of 4 times the width of the model, and I need to tell it how big its vocab is. Let's say it has 300 possible tokens, and it can be trained on sequences of length up to 50. These are all kind of arbitrary choices because, I don't know, there isn't really a canonical way of doing things for this experiment. I'm mostly just YOLOing and seeing what seems kind of reasonable. So, defining the model, and now I want to, and it automatically moves it to my GPU, which is delightful. And now I want to define a deactivate position function where, so internally, this model is using standard learned positional embeddings by default. So it has this layer called PosEmbed, which may be fun to look at the code for. So yeah, so this is the positional embedding layer, and it's basically just got this learned weight matrix, and then you feed in tokens, and it just indexes in whatever the appropriate thing is for the tokens. Here we just got length of tokens offset by some shader for caching, and it just returns that and adds it to the residual stream. So to disable this, it would suffice if I just set self wpos to be 0 and made it so that it never gets updated. And that seems like a thing that I can probably just do. So this should just set everything to 0, and once I've done that, it's probably sufficient to just set it. Oh, beautiful. Copilot just knows how to do everything for me. Yes, PyTorch has this wonderful requires grad that I can just set to be false. Everything just magically works. And yes, I predict that if I do this, the positional embeddings will both be 0 and remain 0. Though I should probably check this at some point. But, what? So, I don't know. How can I check this? I can just define some random tokens. 1, 2, 3, 4. Put this on the GPU. Define some basic optimizer. With a really big learning rate, because that should make any movement incredibly obvious. And then take loss equals the logits added together. And let's just, run this a bunch. So at the start, I want to print what the positional embedding is, and great, that remains 0. I'm happy. Oh, and let's just check that other matrices do not remain the same. Well, it's become nan for those rows. Good enough for me. Alright, I'm going to cache this as yes, my turn off the positional embeddings function works. Alright, so now I want to define the data. This should be pretty easy. I want to define a so let's see. First I should probably just also add in a bunch of variables for various kinds of training config. Well, no, I should probably just add a section after data to define exactly how to start with model training. But okay, so I want to define a data generator. It's probably fine if I just reuse the context length and vocab size that I defined within the model config. So let's just input in a config variable, and other things I care about are going to be batch size, and I guess probably literally just batch size. Maybe include beginning of sequence token, and let's set that to true by default. But okay, so what I want to do, I want to let's see, probably set the seed for this function as whatever the seed within my config is. So it's, I know, a bit more deterministic, and then go and, well, Copilot did everything for me. Wonderful. And as far as I can see, this code is basically just correct. Fascinating. Alright, so now let's just test that this is doing something sensible. Those basically look like random tokens. Oh, and the final thing that I need to do is define a loss function. And for this, I'm going to want to take in the tokens and take in the logits. And now I'm kind of going to be doing the opposite of standard cross-entropy loss, because here I'm going to be taking the logits of everything but the first position, and then so let's see, it's logit shape tends to be batch by position by vocab, token shape is batch by position. Copilot, done it again. Generally, just a pretty useful heuristic is always know the shapes of all the variables you're working with, and if you're using libraries that make it hard to keep track of the shapes, those are bad libraries and you should use inops instead. But great, now I know what the shapes are. I can just be like, I do not care about the logit on the first token because it has no previous token. I do not care about what the final token is. And now I can convert this to log softmax. I convert this to log probs and get the correct log probs using torch.gather, which is this kind of fucked but yet incredibly useful function, which says exactly what gather does is kind of convoluted, but it's basically saying pick some axis of your function, here the final axis, input in a tensor with the same shape as your original tensor, except possibly on this axis, where each element of the tensor you're feeding in is an element of the new axis, and then it feeds out, it returns something that has the same shape as tokens, the thing you fed in, but where the entry in the position of tokens is the thing corresponding to that in the original tensor, but where the value in that position is the index you take in there. And that was a kind of convoluted explanation. Go read the docs for torch.gather if you care. If you don't care, just take my word for it that this is valid code that will get me the log prob for the correct token. And yes, an often useful thing to have on loss functions when I'm trying to do detailed analysis is to have a flag where I can return the per token correct log probs. So if return per token, I just want to return the entire thing. Otherwise, I want to return the actual log prob, the actual log loss. Often this is useful for analyzing things like, are there specific tokens where it knows how to do it? If the model has good but not amazing loss, is it the case that it's mediocre on everything, or it's perfect on some and terrible on others, etc. So it's just a useful thing to have around. And yeah, what next? So yes, I should probably test this loss function. So let's say my test tokens are, I know the numbers from 1 to 5, And let's say my test logits are, yeah, let's say they're random normals, but that I set, let's see, let's make the first entry 1, and then let's take my logits and let's set the corresponding entries to be really big. So like 1, 0 is going to be 10, 2, 1 is going to be 10, 3, 2 is going to be 10, and 4, 3 is going to be 10. And then let's print the loss function, both with per token is true and per token is false. And this doesn't like me. Oh, it's because I forgot the batch dimension existed. And it's because I forgot to run the previous cell. Joy of actual coding. Great, that's an incredibly low loss. I am happy this function works. So now I want to set up the optimizer, and this is basically just going to look like figuring out what sensible variables are. Let's say my batch size is 64. I'm going to train for 10,000 epochs, randomly generated data each epoch, so I know you can kind of think of it all as being a single epoch, where everything I'm calling an epoch is a step, but like an epoch is a single batch. I don't really know what sensible hyperparameters are, so I'm just going to kind of YOLO and type in vaguely reasonable things. But I probably don't care about having weight decay. And yeah, empirically, I sometimes get better results with a learning rate scheduler that just warms things up for the first, like, 100 steps. So YOLO, let's try that. I don't really know how to figure this kind of thing out in a principled way. But yes. Learning rate schedulers, you just give it a function that takes in the step number and gives you a thing to scale the learning rate by. This is just going to go from 0 to 1 linearly and then be at 1 forever. And I want to define the data loader, which is just going to be data generator model.config, and what did I do? Oh, this is a markdown cell, not a code cell. Wild. Great. Turns out having variable names the same as your functions is bad. Who would have guessed? Okay, so now I want to try training the model and see if this entire setup was just kind of fucked or not. Let me just double check that I defined my model correctly. Probably it would be good if I just actually printed the model and just checked that it looks vaguely the way I expect. Great. Oh yeah, looks like I got the model set up by default to not use LayerNorms, or at least to have LayerNorm set the identity. I feel fine with that because I hate LayerNorm. All of these various hooks I have in there are this dumb hack that lets me actually access and edit the activations within a model, which, due to PyTorch fuckery, the easiest way of doing that is you just define a layer that does nothing, that wraps around an activation, that you can now attach a hook to, and this lets you just access and edit and cache every activation really nicely. It's very weird. But, okay, so let's try to actually train the model. So let's make some list to track my losses. TDDM is this fabulous library that gives me progress bars, and let's say I probably want to rename batch to be tokens. Side note, Control D is just my favorite command. I can just copy instances of the same text and edit it. It's wonderful. Yep, blah blah, standard PyTorch boilerplate. And know if epoch is 100, print out what the loss is. Cool. And yeah, because I'm training on randomly generated data, that's totally fine, and the model will just figure out how to do things. Because I'm training on randomly generated data, I can just have a list of losses, and this is fine. And it will let me, I don't need to have train and test loss be separate. And let's print at the end, the training curve. And I don't really care about having a title. And let's put in a button to toggle whether the x and y axes are log or linear, because that's, yes, line is a function from this custom plotting library that I wrote, which is basically a shitty wraparound Plotly that makes Plotly do the things that I want slightly more often. And yeah, let's see what happens. So staring at this, I am like, A, that's getting pretty good loss, and also B, that was weird. Why is this model having loss spikes? Alright, so it'd probably make my life easier if it wasn't having loss spikes. One random idea that might help is adding gradient norm clipping. So let's restart all of this and do that. And I'm just going to quickly Google how to do gradient norm clipping on my other monitor, because I can't quite remember the syntax. Great. So, roughly, gradient norm clipping takes a model and says, if any of your gradients exceeds this amount, I'm just going to reduce them till they reach that amount. And empirically, this seems kind of helpful. I don't know. Let's just plot the loss curve and check that I'm correct, that it has lots of dumb spikes. And while that is inexplicably taking a long time to plot, I'm just going to go and write the gradient norm clipping stuff. So yes, this line just defined, so I can turn off gradient norm clipping later if I so choose. And yes, Plotly is so janky. Okay. I did not even notice how fucked this model got at the end. That is kind of impressive. Okay, let's see if gradient norm clipping will magically fix this. Oh wait, no, I should reinitialize everything. I should definitely reinitialize everything. How did that happen? I have never seen a model get to over 5 trillion lots before. Okay, so let's run all and alright, let's see if we continue to get random dumb loss spikes. Alright, while I wait for that to train and see how fucked it is, let's make a start on actually writing code to interpret this. What? What? I did not hit keyboard interrupt. What just happened? Oh, let's run everything again. Yes, hopefully this is an insight into the level of random dumb shit that happens when I'm just writing code. But, okay, so I want to look at attention patterns in my model and see what's going on. So the key things to do are basically to just give the model a bunch of data. I don't know, let's just make a big data loader. Man, Copilot, so great. Let's change... Yeah, probably be good if I explicitly added the option to put a seed in there, so I don't just accidentally get the same things because it had the same model seed. So yeah, let's go here. A convenient thing of working with tiny models is that we probably can just like run them on a load of data and see what happens. Copilot is telling me I should be doing things like doing model.eval and model.train, but nothing in my model changes if I tell it to train or not, so who cares? Alright, so this model sure is still having loss spikes. Oh god, that is a bad loss spike. Why does this keep going to 1 trillion? Okay, so new idea. Maybe actually having LayerNorm is useful. What is even the name of the command that I defined? To do LayerNorm normalization type. And let's see, is there anything else that seems like it could help with this? Oh, weight decay. Weight decay seems probably good. Yeah, and maybe let's increase my second atom beta, because that should make things smoother, because it will mean that if there's dramatic changes in the gradients, then the denominator is going to be pretty... Oh, I slightly retract that logic. So I guess a reasoning about how atom works, if I'm assuming that loss spikes come because there's some weird data and the model has a really big gradient on that data that sends it in a weird direction, if atom has a really big second beta, so the way atom works is it has It's got these two buffers. One of them is the kind of is essentially the like average gradient. I don't know. It's basically trying to estimate what is the expected gradient, and it does this with an exponentially weighted moving average, where it's like u previous times beta 1 plus gradient times 1 minus beta 1. And then there's a second buffer, the second order one, which is trying to estimate the expected value of the gradient squared. This is an element to y squared, which is completely fucked, but whatever. And probably shouldn't use sigma, because sigma is normally the variable for standard deviations. So let's call this v. And in practice, v is previous v times beta 2 plus gradient squared times 1 minus beta 2. And so a prediction would be that if we suddenly had, and then the atom update is, it changes the parameters by taking the average gradient and dividing by the square root of the average squared gradient and then multiplying by the learning rate. And so under the hypothesis that loss spikes are caused by like some massive gradient causing the model to do really dumb shit, under this model, if this gets really big, mu is going to be dominated by 1 minus beta 1. If this gets really big, v is going to be dominated by 1 minus beta 2. And so maybe beta 2 being really close to 1 is going to make the denominator small in a way that screws things. I have no idea. But based on this logic, I'm kind of like, maybe let's lower this to 0.95 and see if that changes anything. So, I don't know. That's a bunch of changes. What happens when I apply these changes? Oh, that's such a stupid loss curve. I love these buttons. Alright, so looking at these buttons, I'm like, it sure just kind of seems like loss just goes continuously up for a while. That's kind of weird. Well, let's try to figure out what's going on. I'm going to take a quick break while that... Alright, I'm back. Let's see how much of a mess that was. So this definitely still has loss spikes. Well, so it has loss spikes, but like early in training, it's kind of fine, and then shit starts getting weird. So I guess the two choices I have are I can continue trying to figure out what the fuck is up with the loss spikes, or I can just be like, let's just stop training there and call it a day and try to interpret that model. These both seem like pretty reasonable options, to be honest. What? What is going on with this model? I'm so confused. Okay. I'm going to make one more attempt for dumb ideas that might help. Specifically, making the learning rate lower and the batch size larger, so it's less likely to do random dumb shit. And if this doesn't work, I'm just going to say fuck it. And yeah, let's do like 4,000 epochs this time. And if this doesn't work, I'm just going to do everything and just do the pick a snapshot that has good performance and call it a day strategy. Alright, how fucked is it this time? It's going pretty strong. I'm just gonna pause recording until it's done. Hey! Alright, so the model is trained, and you can make two observations. One is I've like mostly, but definitely not entirely solved the loss spikes, and also have definitely not figured out why the fuck the loss spikes were happening. But this is kind of non-central to my project, so whatever. And the other interesting observation is that the model just clearly has learned how to look at the previous token, which is probably the interesting observation from the very start, other than massive loss spikes tangent. But, okay, so let's go and actually try to interpret the model. So, first dumb thing to check, is it the case that the model's positional embedding is, no, it's like the norm. Check that everything's still 0. Because this sure would be embarrassing to learn that. Beautiful. Next thing, load a bunch of data. I know 4,000 data points seems kind of reasonable. Then I want to run the model on this. I'm going to use a utility called run with cache that will return both the model output and an object which contains all of the cache activations. And then I want to print the loss on this, and I'm going to try to plot the attention patterns. Generally, because this is fundamentally a problem about moving information from the right previous positions to the current position, it seems plausible that the way models are going to do this is by... Oh, it seems like the only way the model can be solving this problem is by learning some ways of moving information from the right positions to the current position, and understanding how it does that is going to start by looking at the attention patterns and just checking that they're basically doing what I expect, and then I can try to dig into how they do that. So, okay, let's print out the loss and check that it looks sane. Oh, fuck's sake. Oh, it's because I wrote big tokens.cuda, not big tokens equals big tokens.cuda, and tensors do not get moved in place even though models get moved in place. Okay, so now I want to plot the attention pattern. The dumbest way of... Let's just do this for like let's just do this for like the first element of the batch. There's just an illustrative example to start to get our hands dirty and like what concretely is going on. And let's see. So the attention pattern for the head in layer 0 is going to look like this. Yeah, probably good to just print out what keys are in this cache object. And for some reason my Jupyter notebook is becoming incredibly slow. Great. So this is a list of keys. Each key corresponds to a different variable. The key variable here is this hook attention, which looks at the attention pattern, and I can either get it out with just literally its name, or with this utility where I can just give it the name of the activation and the layer, and it figures out the rest. And let's just look at the shape. Cool. So the shape is batch, by head index, by position, where this is the destination token, where information is moved to. This is the source token, where information is moved from. I'm just going to take the first element of this and ignore this. So, because there's only one head per layer. So I'm going to display that, and what do I want the x value to be? Probably I want the x value to be like a string version of the tokens. And there's this random dumb thing where if you give Plotly non-distinct labels on an imshow, it thinks that means that you want to combine the cells with the same label into the same value. I don't understand why, but this means my standard hack for a shitty image visualizer is adding as a label the index of that token. And okay, so this is interesting. Cool, so this is a very striking pattern, and it basically seems like this head is clearly treating the first token in a special way, and it's treating the other tokens as much less special. It seemed to be approximately uniform over the other tokens. And so, like, my guess looking at this is it's learned to... Yeah, my guess would be it's learned to attend, I don't know, somewhat more to this position than every other position. It's learned to attend... So this head can only access the value of the token at the destination and the value of the token at the source. It can't take into account anything else because I didn't give it positional information and because this is how attention works. And so it's clearly learned to pick up on the fact that the first token has a special token value, even if it can't tell where it is relative to that. And then learned to do something so that its attention score for every other token is equal. Its attention score for this token is some other number. And then, I don't know, if this is like 10x all of these, and you do a softmax on that, this one is always going to end up bigger, and these are always going to end up basically uniform. So I think it makes sense to me that this is a function that the model could learn. I'm going to assume it's doing something with the MLP to make this useful, and let's plot the second head as well. And interesting. So this head has definitely learned to do some... Well, so it's definitely learned to do localized position, which is exciting and interesting. It also significantly attends to itself, which is kind of unexpected. But at this point, the model has clearly learned how to think about positions. And yeah, it's got the most attention paid to the current token, and then it's got a good chunk of attention paid to the previous token, and then things drop off very sharply and is basically negligible. And I don't know, it's kind of interesting. Let's just try a bunch of... Oh, well, under the assumption that these patterns are basically independent of the actual token values, it seems like we should be able to, rather than indexing into the batch, it seems like we should be able to just average over the batch and get the same result. So let's average over the batch and head index dimensions. Averaging over the head index dimension is kind of irrelevant, but means I just have to think about it. And cool. So this is the average, and it basically looks exactly like the first one, which suggests that the model is roughly doing something of the form learn to ignore token values when figuring out where to attend to. And okay, so the next question I want to ask is, how are the logits calculated? Where my naive picture would be, you take each of these heads, you take the head in the final layer, the head learns to attend to the previous token, and then it copies that to the current position, and that's just directly added to the logits. I am now less confident this is what's going on, because... Sorry. I am less confident that this is what's going on, because it's also significantly attending to itself, which is interesting, and suggests that it's going to have to be doing something to distinguish between the amount that the head is contributing to the current token because the current token is there, versus the amount it's contributing from the previous token. And plausibly this is something that it needs the final MLP to process. Ultimately, given that it already has the current token in the residual stream, maybe it just learns to do this in a way that just totally cancels out. I have no idea, but I am kind of curious. So the way we figure out how different bits of the model contribute to the logits is, so the logits are going to be the sum of the residual stream, the logits are a linear map from the residual stream. The residual stream is the sum of the output of each layer, which are going to be basically these 5 things. The embedding, the first attention out, the output of the first attention layer, the first MLP out, the output of the first MLP layer, I have no idea why the text on my screen is light blue, but whatever. Wait, no, I should really zero index, otherwise everything will get incredibly confusing. And so now a thing that I can do is take these residual components and just wait, no, scratch that. Now I can take each of these residual components and map just those to the logits and see how much they contribute to the correct logit. And this is... yeah, let's start by just doing this for just the first token index, because it's a fair bit more of a pain to do this. I love Copilot. It's a fair bit more of a pain to do this across an entire batch, and it will involve thinking more about fancy indexing. But, so, let's just print the shape of resid stack to check that it's roughly what I expect. Great, you've got a components dimension, a batch dimension, a position dimension, and a residual stream dimension. So now I want to just look at this for the first element of the batch, because then my life will be easier and the lessons will probably generalize. I want to at the unembedding matrix, and that should convert this 64 into a that should convert this 64 into the vocab, though it occurs to me that I actually, because I use LayerNorm, this is slightly more complicated. And so an annoying thing about LayerNorm is that the fact that it's followed by a linear operation of scaling by the weights W, and then followed by this matrix multiply, the element-wise scaling with these weights is actually equivalent to multiplying by a diagonal matrix from these weights, which means that you're essentially multiplying by two matrices, and to only really make sense to study the combination matrix. I also need to divide by the scaling term on the LayerNorm ln final, which is the one just before the unembedding. Scale is the cached amount that the LayerNorm divides things by. And I guess I also probably need to remove the mean if I'm being fully rigorous, which I can just do up here because everything's using LayerNorm, so none of these things matter. And yeah, so reset stack. This is a useful idiom, which just basically means take the final dimension, take the average across it, keep that dimension so that everything's going to broadcast nicely, and subtract, which basically means take every final dimension column and set that to 0, keeping everything else the same. And great. I think that this now should account for everything that I might care about, and I can think of this as the Logit components, which should be a component dimension by position, by vocab dimension, tensor, and what? Oh, it's because LayerNorm is also an enormous tensor, and so I'm getting annoyed complaints from my code. Also, just generally observe, there is a great amount of random monkeying around with tensors and sizes and getting all of my indices right. And this is just kind of a fundamental thing of doing ML code, and it's kind of a mess. This is a solid idea. I wasn't planning on doing that, but Logit's a translation invariant, meaning when you add 1 to every Logit, it doesn't change the log prob. So often when you're trying to interpret Logits, it's pretty helpful to subtract off the mean, because this is a pretty crude way of just getting rid of effects that look like adding 1 to everything. And yeah, so now I want to index in to the Logit components with the correct final token. And now an interesting question is, do I remember how to do this? Where I think if I have my fancy indexing correct, if I put in an array here of indices and an array here of the same length, then this should just work. And so here I want to take a range from 1 to the max, and over here I want to take a range from 0 to 1 below the max. And I think that if I haven't fucked up my indexing, that this should give me the correct Logit attributions, and then I can just do an imshow on that. And now probably easiest if I just do a line graph on that, and hopefully this will then just show me what's up and how much different parts of the model contribute to the correct output. And now I wait because Plotly is being weirdly slow today. Alright, so I should put in labels. Oh wait, I defined labels earlier. But surely find a way to fix that. Okay, so looking at this, it seems pretty obvious that MLP2 is doing most of the work here. Well, yeah, basically all of the work here. And another interesting point is that I have no idea what I was saying there. Alright, so MLP2 is clearly doing something, and it's contributing to the logits. And so the remaining mysteries I have are how on earth is... Yeah, so mystery 1, what's going on here? This should be pretty easy to figure out. Mystery 2, how the fuck does it get positional information in here, where it's presumably doing something intelligent with this output of the heads, and maybe something intelligent with these. And then there's the question of how on earth is this output put into the MLPs in order to get something out that's the correct previous token? And also, why does it need MLPs at all? This is kind of a bunch of things. So let's scrap this previous structure, and then let's just break this down into understand attention 0, understand MLP 0, except make that a header because then everything looks nice. Why is this fucking markdown? Oh man, I used a different heading size. This is the worst. Alright, so this is my game plan. So how should I go about actually trying to understand attention 0? So now we can just basically just vanilla apply the ideas from the Transformer Circuits Framework paper. The attention pattern is determined by the product of WQ transpose and WK, the QK circuit, and the attention is basically purely determined by the full QK circuit, which is so let's see. Alright, so this is going to be a pain because basically everything I'm going to do is going to involve folding in LayerNorm, because if I don't, then all of the weight matrices that I'm going to want to play around with are just like slightly inaccurate. So what I'm going to do is I'm going to use some utilities I have in the model for folding in LayerNorm. So let's create a second model called my analysis model, and let's fold in the LayerNorm, and I'm going to take a brief break to go read my code and figure out how to. Great. Okay, so I just have this beautiful function which says take a model and load in a state dict and do a bunch of things to clean up what's going on there. And so I'm just going to go and exactly do that. So I don't care about initializing the weights. I'm going to define the model. Then I'm going to take the state dict of the trained model, and I'm going to load and process that into this analysis model. And this has a bunch of nice helper functions that will do simplifying things to the model weights that make no difference to the actual computation the model does, but generally make my life easier. And I should follow this by deactivate positional embedding, just to make sure that I haven't accidentally introduced positional embeddings into this new model. But yeah, I should get out of this a model that is nicer and simpler while also computationally equivalent, and I can check this by comparing the loss on big tokens. And checking that these are exactly the same loss. It sure would be a pain if they weren't, because I then need to go and debug things, and that would be annoying and not quite conducive to me attempting to dynamically stream myself doing interesting research. Oh wait, these are the model logits. So yeah, just going over what the simplifications are. The fold LayerNorm command. The fold LayerNorm command tells the model do the operation we did up here, where you combine the LayerNorm weights with the weights of the linear layer immediately after to kind of create an effective linear layer where you can then ignore those weights, and do a similar thing to ignore the LayerNorm biases. This says take every set of weights writing to the residual stream and then set their mean to be 0. This should make no difference because LayerNorm always removes the mean anyway when it reads from the residual stream. And center unembed says make the output matrix have mean 0, like the unembed. And this is pretty worth doing because of the point I made earlier about how the logits are translation invariant, and this just removes a bit of useless information you might be looking at. And the losses are identical, so I'm going to call this a success. And also, this is an update that I should define a utility function that does this for me, because this is just clearly a useful thing to be able to do in a low friction way. But okay, so now we're going to try to understand what is up with attention head 0. And so we want to define the QK matrix, and the QK matrix is going to be the product of the query matrix and the product. Sorry, it's going to be the product of the embedding, the product of the query matrix, the product of the key transpose, and the product of the embedding transpose. And this is going to get me a vocab by vocab matrix that's basically a big bilinear form that takes in a pair of tokens and gives me a scalar. And this basically represents a massive lookup table of what the model does when given various inputs. And I think that if I do this, I should just basically be able to read off that the model learns to pay a bunch of attention to the beginning of sequence token and a equivalent and equal but lower amount of attention to all other tokens, creating this funky ass pattern we saw earlier. Also, I probably just want to take a moment to just appreciate how pretty this pattern is. It's so unexpectedly elegant and graduated. It's great. Alright, so what the fuck is this? Alright, so I should probably label my axes. So the y-axis is going to be query. The x-axis is going to be key. Title is going to be full QK circuit. Full QK circuit for attention 0. It's just a single head. Normally this would involve several heads. And yeah, interesting. So I'm kind of confused because these are incredibly small numbers, and this makes me wonder if I've screwed something up and have a bug. Oh lol, I'm using model rather than analysis model. Okay, this is gonna just be really annoying. So what I should instead do is store a copy of the old model and then rename model to be analysis model. At the cost of fucking a lot of the earlier code if I ever try to rerun it. But this will make my life much easier. Great. Alright, this looks a lot more reasonable, and this is an important lesson in the virtue of actually doing all of this shit to try to interpret things, because if you don't, your life is pain. So I'm kind of surprised that everything is so small. But other than that, this does basically match the prediction of this is big, everything else is much smaller. Though, so I do also just find this kind of hard to reason about, because these are, so like, I don't know, these are varying up to like half of a thousandth. These are kind of oscillating around 1 to several thousandths. I'm kind of surprised there's that striking a color difference between the two, to be honest. But I don't know. I feel like my overall question of how this works has been broadly answered, except for this general confusion about this seems too small, what? But probably I just have some bug somewhere. Okay, so the next question is, what is up with the OV circuit of this model? And so the standard thing we do in a one-layer attention-only model is multiply out to the unembed. Note that this is slightly an abusive notation. Really, it should be model.embed.we, but I just added model.we as a wrapper because it's a bit more convenient. So normally, if we were doing the standard transformer circuits framework thing, we would multiply by WU to get the model's effect on the output. In this case, the thing we care about is probably the impact on MLP 0. So let's just do that instead. And this should give me a vocab by neuron matrix. So let's plot this and see what happens. Yes, note the meta point of just plot shit. It's really useful. Visualize everything. Have low friction functions so you can just visualize things as you go and see if you learn interesting things. Cool, well, that's interesting. So this basically seems to be telling me that most neurons don't matter and aren't really affected, while some neurons matter a lot, and that okay, so it looks like the top row matters. Yeah, so my inference from this is most neurons just don't matter that much and don't have that big of an effect. And then there's lots of neurons that have like a kind of pretty wide and diffuse input from everything else. And then this is pretty sharply different from the input value. And it's like, I don't know, it's kind of difficult to interpret. I just want to go and actually look at the MLPs. And so because this is ReLU, in some ways this is kind of nice because we can... So the standard thing we always have to look at in an MLP is the actual values. But we also have, with a ReLU, we can just look at, is it on or not? And this might be kind of interesting. And yeah, I guess I don't really have like a super clear idea of what I'm doing with this, with the MLP interpretability section. Interpreting MLPs is kind of hard, but there are probably some pretty dumb things that I'd want to check. Like, is it the case there is some MLP that just only activates on position 3, or some MLP that only ever activates on position 4, or something like that? And so the two dumbest things that I might want to do are plot the MLP for my single input. Then this is going to be a position by neuron tensor. And then I want to do the same thing, but this time just averaging over the entire first position. And Now I want to do the same thing, but rather than looking at the actual neuron value, I want to look at, is the neuron value positive or negative? And that is the easiest way of doing that is just saying, like, is this greater than 0? Then there's a minor pain because lots of PyTorch operations like mean are not supported for booleans, but if I cast everything to a float, it should be fine. And let's call these neuron firings. Why is my plotting function so slow? This is not that big. But alright, so in the meantime, let's think about what do I predict is going on for the MLP neurons. So what I predict is going on is that there is just going to be like 1 or 2 neurons per position that fire strongly for that position. Oh, rip. So yeah, no, that was totally my bad. The thing that I want to call things is post, for post activation, and I do not have a hook called hook MLP, and maybe that's why things were breaking and Jupyter was just taking a really long time to tell me I had an error. I have no idea. But let's see if it's less sad now. Great. Ooh, what? So this is weird. So, So this is the neuron activations for this single input, and it's definitely not the case that there are just neurons that fire for each input or anything like that. Instead, you get these fascinating neurons that are kind of graduating how much they fire. Oh, this is super cute. Okay, so let's, I don't know, I kind of want to just plot some of these and see what the line looks like. Like, is this linear? Is it dropping off in a more interesting way? So, like, I don't know, this is neuron 83. What does neuron 83 look like? And yeah, so it basically feels like neuron activations averaged over all inputs looks pretty damn similar. Yeah, maybe there's some neurons that are vaguely tracking things like actual information about the tokens that are kind of random scatterings like this, and then when we do this smooth averaging, it's like, screw that, I'm just going to keep the positional information. I guess one test I could do to distinguish between these is try intervening on the model to feed in these average activations instead of whatever activations it actually has on a given input, and see how much that changes things. That actually sounds like a pretty interesting experiment. I'm just gonna go try that. Yeah, let's add a bonus section at the end. Experiment. So So which activations so I guess the really dumb way of doing this would just be make a list of all of the activations I can access in my model. And there should be an attribute called a hook dict, which gives me this. Yeah, so this gives me a list of hooks. And then for each activation name, so let's generate a new token batch as the next thing in big data loader, or whatever I called that. And that's to verify that our model gets pretty good loss on this. And so now I want to write a function which can take my model and then intervene on each position to intervene on a specific activation to replace the value of that activation with an average value across all the activations in this batch. And so the way I'm going to do that is, so the syntax for this in Easy Transformer is defining a hook function. So let's call this replacing hook. The two terms in the function are the input, are the activation, and the hook that this is acting upon, which is just an object with some useful parameters, none of which I really care about here. And then I can also just write in some variable in this, in global scope, call it replace act, and let's say that's the thing in cache for this hook, and then average over the batch dimension, and then I can just replace in this activation that with this averaged activation. Let's rename this to average act. Note that I have averaged over the batch dimension, but I have not averaged over the position dimension. Averaging over the batch dimension tests the hypothesis, so there's nothing meaningful about actual token values. The only thing that's meaningful is position. And yes, this will have gone down a dimension because of the mean, so I need to get it back up to be the same size as the activation, and I'm going to do that using inops, which is my favorite library for this kind of thing, where this syntax means take something with any number of dimensions, increase it to repeat it so that it's got a new dimension of size batch at the start and is otherwise the same, and then I can just tell it batch should be whatever the size of the first dimension of new token batch is, and yeah, by editing the activation and returning it, we can intervene, and now we can run the model using this run with hooks function. And what we do is we give it in a list, which is a pair of tuples of hook names, a pair of tuples with hook names and the actual corresponding function. It will run the model with this hook in there temporarily, but will replace the hook. It will temporarily add in the hook, run the function, and then end. And we can... Oh, I should... Yeah, because I'm currently doing a bunch of analysis, I think it would probably be useful if I just turned off autodiff everywhere. Annoying gotcha in Torch is that every time you do any computation with a tensor that has track my gradients enabled, the model will, the underlying Torch engine will track every tensor that was involved in computing that, in case it needs to use it to do a derivative later. This is kind of a pain, and means that things will remain in memory a lot longer than you might expect. So when you get to the point where you're no longer training a model, it's often sensible to just deactivate it. Though note that you are editing global scope, and so this is kind of a hacky pain. But alright, returning to the experiment. So I've got this average activation. For some reason, VS Code thinks this is an error, even though it's clearly fine. And what? How has this been running for 5 minutes? What the fuck is wrong with my VS Code? Alright. Probably the most reasonable thing to do at this point is to restart my kernel and retrain the model and hope that things broadly work out in the same way, and then also make sure I save the model weights this time. I'm just gonna pause while I go and do that.